Hi, everyone. My name is Umang. I am a lead data engineer at Chartmetric. We are a startup primarily based in San Francisco, New York City, and Seoul. We work on music analytics, and I'm a lead data engineer here. Um, I've been with the company for about 5.5 years, and I work mostly on the data infrastructure at our company. So what we do is music analytics. So this is our web app where we show our data to our customers. We collect data for a lot of tracks, artists, albums, playlists, curators, basically a lot of music data. Our customers tend to be artists, record labels, band managers, more indie artists, and we can show them how their artists are doing, performing to their peers, their contemporaries, how they rank and are segmented in their career stage. So for example, here we can see Imagine Dragons and their contemporaries as well as, well, other peers as well, broken down by other career stages, especially developing artists, which are very important for record labels as they are identifying new artists. The key data for our platform comes from streaming platforms, social media, charts. So we have data from Spotify, we have data from TikTok, which is pretty big in the music industry, Instagram, Billboard charts, Snapchat, which is something we recently have been working on, as well as global music platforms as well. So this is an example from our website where we can compare different artists. Here we're comparing how Spotify monthly listeners, we're comparing Spotify monthly listeners for different artists, including Taylor Swift, Justin Bieber, and others. So talking about scale, we have an application as well as an external API, as well as a small public API offering as well. We basically average around 300K, a throughput of 300K per hour, which comes out to around 80 requests per second. And then on the data side, what this amounts to is we track 12 million artists, 140 million tracks, 45 million albums, and almost 30 million playlists. These numbers are growing rapidly, so we grew by 13% in artists just in a year, so the data are rapidly growing as new artists come on Spotify, Apple Music, Amazon, and other platforms. So before we started using ClickHouse, which we really started looking into early in 2024, this is what our data infrastructure looked like and what the problems that we had with it were. So our main database is a RDS, which we use on AWS Aurora, which is a Postgres database. We had 28 terabytes of data in there. It was a lot of accumulated historical data from 2016, a lot of time series data, which we allowed customers to access directly from the application as well as the API. What this meant for us, and the problem with this, was the storage was costly. There was a lot of infrequent data, a lot of cold access data, but it was costly to store this in our RDS. And then the index, obviously. There were many tables where the indexes were actually larger than the table size itself. We also use Snowflake for about the last 5 years, so we have been doing 700 analytics queries overnight, transformations, and so on. Also, as I'm sure many people are aware, Snowflake is very expensive and obviously not suitable for our API latency needs. Another main issue with Snowflake was also that clustering keys can only be set on one set of columns, which, spoiler, but ClickHouse allows better than that. And then we use Elasticsearch for searching, filtering, and document retrieval for our application. And Elasticsearch works very well. I think we've been using it for about 3 years as well, but it is only for specific use cases. And also, as was previously mentioned, writing JSON is not as easy as writing SQL. And then we use Airflow for data orchestration in our data infrastructure. So ETL, sync, replication, all handled through Airflow. Perfect. This is what our ClickHouse usage today looks like. We initially started off with self-hosted on EC2, a very small instance, and then we as we started using it more and more, our usage increased, our infrastructure needs increased. So we actually started using ClickHouse Cloud last summer itself. Today, we use multiple warehouses per use case. So one for the application and the API. So it's a read-only warehouse. One for data science and analytics, which here is idling. And then one for data engineering, which is used for sync, ETL, and so on. So the first major project that we took on last year was migrating a bunch of the time series data from Postgres to ClickHouse, also from Snowflake to ClickHouse, but majority from Postgres and RDS. So we created a script that could convert the table DDLs automatically into ClickHouse style, which worked very well. ClickHouse is very efficient for ingesting new data. So that part went off without a hitch. But the issues we started running into were the table ordering was optimized for the API. It was not optimized for our sync, which meant that our syncing and replication, which often was running hourly for certain tables, was running into timeouts, was running into memory issues, and so on. In Postgres, this wasn't really an issue for us because we mostly used B-tree indexes to handle it. So that's how we started using projections in ClickHouse. Not quite clustering, not quite indexing. They're basically essentially mini tables that are maintained directly by ClickHouse. A good hands-off implementation so that instead of creating, maintaining, and referencing multiple views, it all just lives within the base table itself. The storage, and ClickHouse compresses the data pretty well, so storage is not really an option as well as we implement as we actually have multiple projections for certain tables as we use them in different ways. But there is a caveat. By default, tables with projections don't really support deletes. There are solutions to that, but that is an important caveat that we ran into early on. But as a whole, this provided huge flexibility for us compared to Snowflake's single clustering key. We could access the data in multiple different ways. So as an example, this is our track metadata table. And we order it by the ID column here at the bottom because that's the most frequent way that it's accessed by our API, internal data engineering analytics. Then we have a projection on max modified at as a function. So that helps us with syncing the data, finding out what the most recent row was, and then we can sync any new changes on top of that. And then we have a projection ordered by the ISRC column. ISRC in the music industry is kind of like an ISBN for books or like a barcode, a unique identifier. So when querying by ISRC, ClickHouse automatically uses the projection. Without it, it would have to scan the entire table. So projections worked very well for us, and we implement them in most of our tables. But as a whole, they allowed us to proceed well with the time series table migrations, which worked out great for us. We were able to reduce our RDS storage from 28 terabytes to 18 terabytes after migrating just the 8 largest tables. So this resulted in a 36% storage cost drop, 36% drop in storage cost for RDS. And also, we allow users to see data for all the way back from 2016 to today. If the track or the artist was updated. These queries, like all queries, frequently timed out on Postgres and on Snowflake just because of the sheer amount of data that was being loaded. In ClickHouse, most of this ran within 3 seconds. This is obviously without caching, but versus on Postgres and Snowflake, it would time out after a minute very frequently. The next problem that we were trying to solve was denormalized/flattened tables. We created these for metadata and metrics for an internal LLM tool. An external LLM tool that we are working on where the user can directly type in questions in plain text and see what the data would look like. But yeah, this required creating denormalized tables, and that frequently ran into out-of-memory issues as we were trying to join several large tables in ClickHouse. We had a lot of initial learnings as we worked on this project. we would try to join before syncing the data to ClickHouse. So in certain cases, this was Snowflake. Certain cases, this was Postgres as well. We also tried to limit joins to one table per query instead of trying to join like 5 large tables. And then obviously, we would use projections to speed up the scans when joining 2 major tables. So this also led us to using where-ins pretty well. So initially, when we were just joining the tables together, ClickHouse would actually, because of the size of the tables, ClickHouse would actually return an out-of-memory error. And as you can see on the bottom left, it was actually scanning every single granule of data. Even though in this query, for example, we're only trying to get the track metadata for Taylor Swift's tracks. We changed the query structure using where-in and filtering the data down quite a bit. And then this query ran in under 100 milliseconds, so 98 milliseconds. And then the memory usage was down to 300 megabytes as well. So it ran much more efficiently. And as the explain plan shows, it basically just scanned about 400 granules instead of the 17,000 that it did initially. So we were actually able to take this much further by batching on top of these where-in filters. Initially, so this query is trying to get all of Taylor Swift's tracks and trying to get all those tracks data from 2016 to today, so one of our history tables. That query would initially take 107 seconds if just done as a raw join. It would read 38 million rows and take 5 gigs of memory on the ClickHouse instance. But after setting up batching, here as an example, I use limit phi and offset 0, and then obviously just changing the offsets for batching. Each batch ran in under half a second. It used 44 megabytes of memory, each of them. So it ended up taking 50% less time and obviously over 99% memory reduction. Using this approach, we were actually able to make our denormalized tables scale pretty well. In certain cases, they did take longer than just a regular join would have happened. But again, these are queries that are running overnight, so it wasn't really an issue for us. But reduction in memory was an important goal for us, so this really helped us a lot. The third example that I want to talk about is a very complex use case that we have. So as I mentioned, we have almost 30 million playlists that we support across all 12 million artists that we have. So this is a screenshot from Taylor Swift's playlist section on the artist page in our application. The user can see all the tracks that are across all 30 million playlists, all of her playlisting tracks. So she has her 850,000 tracks playlisting. We allow the user to do a bunch of complex querying patterns, filtering by artist, filtering playlists by artist, filtering playlists by tracks, by albums, and of course, to see one specific playlist data. We allow multiple filtering options, editorial, radio playlists, algorithmic playlists, New Music Friday playlist, for example. Obviously, there's historical data access. We have been tracking the data since 2016. And then users expect rapid updates, especially on Fridays, which is New Music Friday. When Spotify updates many of their top playlists, users expect to see results within half an hour. Otherwise, we get a bunch of unhappy intercom messages. On the data engineering side, this table has a complex ingestion pattern. We have inserts, updates, and deletes on the same table. It has 5.5 billion rows and 15 million new rows daily, and 30 million playlists. So the scale of the problem was quite challenging. When I joined in 2020, this was still happening on Postgres. Over time, we started using Snowflake, and then we started looking at ClickHouse for this as a solution last year. What helped us a ton was the table engine version collapsing merge tree. Basically, what it does is for an update or a delete, you basically need to invalidate the row first using the row active column, and then you insert the new data. So in this example, the track changed its position yesterday from 1738 to 1737. So we have one row with row active 1, then we invalidate the row with row active -1, and then we have the new row for the data. This lives in the table in ClickHouse, like the two, I guess, old invalid rows live in the table. So this does require backend changes. Like they do need to query the table in a specific manner. However, because our table is ordered by a specific set of columns that they are using to query, this actually works very well in ClickHouse. We, of course, have projections on this table as well. As I mentioned, the data are accessed in multiple different ways. So we have a projection on Spotify playlist when filtering by playlist ID. And then we have restrictions on how the track or the album can be filtered using the artist ID. Again, for syncing and invalidating rows, we have a projection on ID and modify that. And then these are the 4 primary columns that we use for version collapsing merge tree. And basically, that's how ClickHouse internally sorts the data and makes sure that there are no duplicates for that, for those 4 primary columns. As I mentioned before, projections don't take up a lot of space, especially because of the compression. So this is actually the full table schema, like the full DDL for the table. There are 31 columns in it. And even then, even with 8 billion rows, it only takes up 340 gigabytes in a compressed manner on ClickHouse. Compare that to Postgres, where the raw data with only 7 columns took up almost exactly half a terabyte. Versus the 340 gigabytes on ClickHouse includes the projections as well, which broken down here show ClickHouse's compression ratio, which really worked well for us. We initially were creating the data for this table on Snowflake and then syncing it every hour. That's when it went live last year. But this July, we actually moved the entire pipeline over to ClickHouse, and we now are able to run it every 5 minutes, which has scaled very well for us. In fact, we run it every 5 minutes, and it frequently takes less than 2. And to compare the query performance, so when we first started considering Snowflake instead of Postgres for this query, Snowflake was timing out usually around 60 plus seconds. And Taylor Swift's data was producing so much data that it was actually taking over 5 minutes in certain cases for her queries. So then we started using Snowflake about a few years ago. Over time, Snowflake wasn't able to keep up as well. And it was taking 20 seconds for certain top artists last year. And then now with ClickHouse, we are able to see performance and results within a second and a half in most cases. That has been great for our application and API. So in conclusion, ClickHouse works very well as part of a multi-system data stack, especially in our case. We still need Postgres to maintain consistency and complex table relationships, foreign keys, reference checks, constraints, etc. Snowflake is a black box for analytics, which works well, but it's also very expensive, especially compared to ClickHouse. So that's why for us, ClickHouse has shown to be working very well in the multi-system data stack. It's excellent for time series data. The version collapsing merge tree was a game changer for us. A speed up from 20 seconds to 1.5 seconds was very significant for us. And large joins can be challenging. We initially had a lot of trouble with them. We reached out to ClickHouse. They were happy to help. But we were able to solve these by using batching and projections, which also make ClickHouse very flexible for us. So with that, thank you. And I want to mention the rest of my team, many of who work remotely across the world. Thank you.